Okay, thank you very much for the introduction. This is joint work with Puya Farshim, and essentially there's three main contributions to the paper and three main sections to the talk. The first is a positive result that relates indifferentiability to related key security that isn't can be applied to even Mansour schemes but isn't restricted to them. The second is that we find some conditions that mean the even Mansour schemes can provide RKA security for up to 3 rounds in the single key case, so you repeat the keys between each of the permutations. And we go on to show that the single key even Mansour schemes can be XOR RKA secure, where you can offset constants into the key, with 2 rounds giving you CPA security and 3 rounds boosting it to CCA. Okay, so start with a brief introduction. So like Yannick said, the iterated even Mansour schemes are a way to build block ciphers from public permutations. And it's kind of interesting from a theoretical perspective that they're intrinsically in the random permutation model, because that's how we're going to model these permutations. The 1 round case, we have just XORing the key either side of the permutation, and we can generalize it to many rounds, either with independent keys between each round, or if we have some sort of key schedule, we're going to follow LED's example and just take repeating the key between different permutations. It's nice and lightweight, you don't have any costs associated with key scheduling, and Barbosa and Farshim last year showed that this gives RKA security for Feistel ciphers, so maybe it's an interesting question to ask whether the same is true for iterated even Mansour schemes. What do we already know about these schemes? Well, for indistinguishability, 1 round with either 1 round or 1 key or 2 keys gives us SPRP security up to the birthday bound, and T rounds with independent keys gives us beyond birthday bound security. The indifferentiability result that's kind of particularly interesting with respect to this work is that 12 rounds with a single key is indifferentiable for an ideal cipher. So that was I think Lomper and Soron. And but up until this point, the related key security of these schemes hasn't really had a formal treatment. Although Colliati and Soron have a paper at Eurocrypt this year that asks similar questions to us with a slightly different emphasis. So what do we mean by related key security? So it was introduced by Beam and Knudsen in the early 90s, but formalized by Bellari and Kono. And essentially their definition is parameterized by this set of permitted functions, RKD functions the adversary can use. So instead of conventionally he'd query M and get back the encryption of M under the key K, now he gets to specify a function phi and gets the encryption of M under the key phi of K. And Albrecht et al. Extended this model and said if we're giving the adversary access to public oracles like the public permutations we've got in this case, then these RKD functions should be able to depend on these public oracles. So how does this all relate to indifferentiability? So here's the sort of indifferentiability setting. You have a block cipher C. So think this is going to be a construction. So think the iterated even Mansour schemes. That's built from some ideal primitive. So this will be our public oracles in this case. And what we want to do is compare this with an ideal cipher and some simulator that tries to cook up what it thinks these ideal primitives would look like if they really were inside the ideal cipher. So what we want to ask is, if we have a scheme where the adversary can't tell the difference between these 2 settings, does this give us any guarantees for RKA security? And Ruston, Shrimpton and Shacham say not necessarily. If you're in a multi-stage setting, then you maybe run into some problems. And the game for RKA security with these oracle-dependent RKD sets is multi-staged. Essentially because you can think of these these RKD functions as sort of little adversaries that have some restricted means to communicate with the main adversary. So what we ask is that if we restrict how these RKD functions interact with the permutation oracles, can we get indifferentiability to guarantee RKA security? And if these RKD functions don't query the permutations at all, then this is kind of like a single stage game, because you don't have phi querying P. So we're okay in this case. Maybe we could do better. And if phi only accesses P via the construction, so it has access to the block cipher, but not the round functions, if you like. So it can do things like sending the key to the encryption of 0, but not K mapping to P of K. This is a much larger class. It's still a very natural way to restrict how phi interacts with its oracles. And we have a theorem that says that this is enough. If we restrict phi in this way, then indifferentiability gives us RKA security. So the next question that we want to ask is, does the one round even Mansour scheme give us any RKA security? So this question's kind of already been asked and answered somewhat in the negative this morning. So what restrictions do we need to put on phi to get RKA security? And Bellari and Kono tell us that if the adversary can predict the output of the RKD functions, then we can never win. There's this very straightforward attack where you make a single query and locally compute what you think the answer should be, and then compare your answers. So we know we're going to need unpredictable RKD functions. Bellari and Kono also say that if the adversary can find two RKD functions that are different but send the key to the same place, then this tends to make the proofs difficult. There isn't necessarily an attack, but it tends to make things a bit more awkward. So we're probably going to want this property. And unfortunately, this isn't quite enough. So here's an example where we've got two elements of the RKD set. So we have the identity and just XORing one constant into the key. This set is unpredictable because if you can't predict the key, you can't predict the key XORed with delta. And it's claw-free because these two functions won't ever take the same value for the same key. But this offset switching attack is well known, has been reported several times. So you make two queries. So you have the identity and have the identity with some message you're choosing, and then you XOR the constant into the key and the constant into the message. And you check whether this relation at the bottom holds. With probability 1 it does for the even Mansour scheme, and essentially never for an ideal cipher. And the problem is that the adversary can query the permutation at the same place twice. So in both cases, you query P at Kx or M. And if we generalize claw-freeness to give to XOR claw-freeness, which says that the adversary can't find two RKD functions that where you apply them both to K and the XOR of these values is some predictable constant. If you have this property, then you can't do this sort of attack. Unfortunately, this isn't enough still, precisely because these RKD functions can depend on the public oracles. And so if you have this set where with the identity and K maps to P of K, this set meets all the previous conditions, but there's still this simple two-query attack where the adversary can work out, again, with probability 1 for the even Mansour scheme, or essentially never for an ideal cipher. And again, the problem is that the adversary queries the permutations at the same point twice, and but this time slightly differently, because his first query, you query P of Kx or K, and then for the second query, it's the RKD function that queries P at K. And so if we have, as we introduce XOR query independence as a property that says this doesn't happen, the queries to P as a result of phi are distinct from the queries to P as a result of queries to E. And the good news is that this is now enough. if we have these 4 conditions, then the one-round single-key even Mansour scheme is RK-CCA secure. How does the proof go? So this is our setting. We have the adversary interacting with his permutation oracle on the left and the construction on the right. And phi at the top is also able to query P. And what we would like to do is replace the permutation in the construction with a forgetful random oracle. So this just gives you independent random values every time you call it, regardless of what the input is. So we need to examine where we might get some inconsistencies arising because of this. And the first one is that because dollar is forgetful, if you query dollar at the same place twice, you won't get the same answer, which you would perhaps expect. And we can avoid this if we assume that our RKD set is XOR claw free, up to the birthday bound, because two queries to dollar at the same place means that x1 XOR phi1 is equal to x2 XOR phi2, and this is exactly the XOR claw free condition. We can also maybe run into problems because P and dollar are supposed to take the same values, but maybe they don't. But if we have an unpredictable RKD function, then the adversary can't do this, again up to the birthday bound, because querying P at the same place as he queries dollar means that at the bottom here, A is equal to X XOR phi of K, and he could predict what phi of K is. And finally, he might run into problems if if phi queries P at the same place as the adversary queries dollar. There isn't a concise way of sort of explaining what's going on here, so to see what the dots are at the bottom, you need to read the full paper. But this is all taken care of with the XOR query independence property. And once we've got these 3, then we can substitute dollar for P. And once we're here, it's fairly straightforward to replace the whole construction with an ideal block cipher, again, up to the birthday bound, assuming that our RKD sets are claw free. And that's us done. The nice thing is that this theorem does actually sort of mean something. The sets aren't vacuous, so we have proved something meaningful. So if you have an XOR universal hash function family, then that meets these conditions. Or if you want to XOR constants into the key and then apply the permutation, that's also okay. Unfortunately, we aren't quite done because the RKD set that we really want is to be able to XOR constants into our key. That was the problem we had with Prost this morning. And the issue here is that this set isn't XOR claw free. This is where the offset switching attack comes from. So can we get XOR RK security from even Mansour schemes? How many rounds do we need? What key schedule do we want? And the first observation is that we're already done. If we know that that 12 rounds with a single key is indifferentiable, and we've got our result from the beginning where indifferentiability gives us RK security under those assumptions, then we're okay. But maybe we can get away with not needing as many rounds. So here's a load of examples that don't work, essentially all because of offset switching attacks. So if you've got a one-round construction, they both fall to it, and then these 2-round constructions, the numbers in brackets are representing the key schedule. So the first one has independent keys, the second one repeats the second key after the 3rd round. And there's one construction that we can't rule out like this, and that's using the same key all the way through. Fortunately, that's enough. So that gives us XOR RK CPA security. And the proof kind of goes fairly similar to the last proof. So the first step, we find these conditions that mean that the 2-round scheme is secure. So we're going to want output unpredictability and claw freeness and XOR query independence. Hopefully not XOR claw freeness. That's the whole point of trying to get XOR RKA security. And a couple of new but kind of similar conditions. And then we want to try and show that XOR constants into the key meets all of these conditions that we need for RKA security. Unfortunately, this technique doesn't give us optimal bounds. it gives us a nice modular proof that's very kind of easy to understand with plenty of structure, but we end up double counting a bad event. So we get some cubic terms, and if you do this analysis directly, then you get rid of this double counting and get tight bounds. There's a couple of ways we can extend these results. Essentially, against all of the 2-round even Mansour ciphers, there's XOR CCA attacks, which kind of are adapted from Andreeva's et al.'s attacks against the indifferentiability of these schemes. But if you do want XOR CCA security, then 3 rounds with a single key is enough. And again, the proof is very, very similar. So those are our 3 sections, and thank you very much for your attention.
Thank you, Gordon. Any questions for Gordon about his talk? No questions? Just a quick question, I'm not sure you can answer. How do your results relate to Yannick's results? For example, Eurocrypt. Maybe Yannick could answer that.
So our XOR CCA results, I think, fundamentally the same. And then they went in a slightly different direction to us. So apart from the sort of one central theorem, the papers are fundamentally distinct,
Okay.
which is quite convenient, really.
Any other questions? Okay, so if there's no further questions, so thank you, Gordon.